So, good morning. Welcome to the Netpore webinar of November. The guest is Celia Tavares de Souza from the Autonomous University of Madrid, Spain. And the title of the webinar is Template-Assisted Nanofabrication of Porous Materials for Energy and Biomedical Applications. Please, Celia.
So thank you very much for your introduction. So first of all, I would like to acknowledge to Netpore cost action and the people involved in this action to invite me to share our work with you. It's really a pleasure for me. It's a very interesting network. I'm working in nanoporous materials since I started my PhD thesis. So I think that I have several things to share with you. There are a lot of people involved in this in the work that I will present you. So I decided to make a presentation that is an overview of the work that I'm involved, that involves several institutions, the Autonomous University of Madrid, the Institute of Material Sciences here also in Madrid, and also the Hospital Gregorio Marañón, where we are performing several biomedical applications using this kind of nanostructures, and also several institutions in Portugal, namely IFIMUP and Requinte at Porto University. So very briefly, I finished my thesis, so I would like only to make a brief presentation about me in order to show you my story, and that then will fit with the presentation and the different works and collaborations that I have. So I finished my PhD in 2011 at the Porto University in collaboration with the Isolde CERN in Switzerland. Then I spent 1 year in Zaragoza University in Spain with a postdoc. So I did my PhD, my thesis in nanoporous materials for biomedical applications, and then I moved to a postdoc in also growing nanostructures and porous materials, but using top-down techniques. Then in 2014, I also had the opportunity to be involved in a project regarding the application of this kind of porous materials that I will show you in this presentation for application in photoelectrochemical solar cells. So now, since 2022, I'm in Autonomous University of Madrid, and so I also show you in the second part of this presentation the work that I'm doing, new work that I'm doing here, also regarding porous templates, but using different methods. So I will start with the motivation, the nanofabrication methods, the three main nanofabrication methods that we use to grow self-organized templates. So in our case, we are working mainly with porous materials, but self-organized porous materials, using mainly three different methods to obtain them. Then I will show you also some strategies to grow high aspect ratio nanostructures inside these porous membranes, in particular magnetic nanowires and nanodiscs for magnetomechanical cell death, and also gold nanorods for near-infrared hyperthermia. So I will focus in these two biomedical applications. Finally, I would like also to show you some results regarding the application of titanium oxide and iron oxide porous structures for photoelectrochemical solar cells. Since it is not my main research line, so I will dedicate only the few last minutes to show you some works that I'm involved in, the groups that I'm collaborating. Okay, so starting with this, why we are working with high aspect ratio nanostructures. So because this kind of nanostructures. So when I'm talking about high aspect ratio nanostructures, I mean that they are not spherical. Okay, so they can be nanostructures like nanowires, but we consider high aspect ratio nanostructures also, for example, nanodiscs or nanotubes. So with this high aspect ratio, I mean that we have a significant difference between the diameter and the thickness of these nanostructures. Part of this work, of our work in this kind of nanostructures, was devoted to the growth of magnetic nanowires and nanodiscs inside nanoporous aluminum membranes in order to develop 3D racetrack memories. We also grown, for example, silver nanowires inside the nanoporous aluminum membranes in order to obtain metamaterials with optical applications. So when we have this kind of silver metallic nanowires inside the dielectric matrix, porous matrix of alumina, we are able to obtain this kind of metamaterials. So instead of nanoporous aluminum membranes, we also applied anodization methods to obtain other types of semiconductors. In particular, we worked with titanium oxide, iron oxide, hematite, the hematite phase, and also tungsten trioxide to obtain photoelectrochemical solar cells with high porosity in order to improve the photocurrent of these nanostructures. And for both plasmonic and magnetic high aspect ratio nanostructures, we apply them for different biomedical applications. And although we worked in these four main applications, the talk today will be focused on biomedical applications of these nanostructures and also for photoelectrochemical applications. So first, before obtaining these high aspect ratio nanostructures, we need to have a porous template to grow inside the high aspect ratio nanostructures. And we use three main methods to obtain these nanoporous templates or these nanoporous membranes that are anodization, laser interference lithography, and Langmuir blotchet. So by anodization, I will explain later in more detail the method of anodization to obtain this type of self-organized nanoporous membranes where we can control the diameter and the length of the pores. We are also using laser interference lithography. With this kind of method, we are able to produce nanodiscs mainly, and we can change the shape of the disc and obtain some kind of squares or triangles or what we want. But in that case, when I'm talking in about in growth high aspect ratio nanostructures, I mean that in principle, the diameter of these structures will be higher than the thickness of the structure, okay? Which is different when we use the nanoporous aluminum membranes, where in the major part of the cases, we can have a high length compared with the diameter of the nanostructure. And another method that we started working recently is the using a Langmuir blodgett. So by we can put nanoparticles in the surface of water, and then we can transfer these nanoparticles to a substrate, and we can use the surface of the particles to grow semi-shells on top of these particles, or we can use the particles as a hard mask and grow antidotes between these nanoparticles, and then remove them and use the holes of the nanoparticles as a nanoporous template to grow the desired material. Okay? Regarding the nanoporous templates obtained by anodization, as I told you before, so we worked with the anodization of different precursor metals. So we anodized aluminum, tungsten, hafnium, iron, and titanium. Other metals can be also anodized, and by optimizing the electrolyte, the applied potential, we are able to grow porous materials with different porosities, different values of porosities, different aspect ratios regarding the ratio between the diameter of these pores and the length of the pores. And all of them usually, when we fabricate them by anodization, we have amorphous materials. But for the case of titanium oxide, iron oxide, hafnium, and tungstenium oxide, we can perform some annealing to convert them in the respective semiconductor material. So in the case of titanium oxide, we used this material for application in die cells. Now we are working with the black titanium oxide also to apply them for hydrogen production and for photocatalysis. We also used iron hematite porous templates for application in fuel cells, in particular in photoelectrochemical solar cells, and the same for tungstenium trioxide. And in the case of nanoporous aluminum membranes, so after it's not possible, or we didn't use it as a semiconductor, so we used the nanoporous aluminum membranes only as a template to grow high aspect ratio nanostructures like nanowires, nanodiscs, and nanotubes inside these membranes. So we use it only as a porous template to grow other types of materials. And for all of them, how we can perform the anodization. So it's a very simple method. So we have a metal that is the anode, and then we use a cathode, an inert material that can be platinum or another inert material, and by applying a voltage between these two electrodes, and by choosing an appropriated electrolyte, and playing with the temperature, time, and also the applied anodization voltage, we are able to grow, instead of a continuous oxide layer, we are able to fabricate nanoporous materials. We can monitorize the current during the anodization process in order to see if we are obtaining porous structure. So if we have a continuous oxide layer, we have a behavior more or less an exponential decay of the current. That means that we are producing a continuous oxide layer with the and increasing the resistance of the porous structure. But when we observe this behavior, where we have an increase or a decrease of the current during the anodization process, that means that we are increasing the resistance of the sample. That means that we are creating a first layer of oxide. But then, since we have an electric field assisted oxidation and dissolution of this oxide, we start to grow the pores at the bottom of the rugosity of the sample, where we have the high values of the electric field. So the pores start to nucleate at these points, and we start to grow, so to decrease this barrier layer of the oxide, increasing the current density, and then the pores start to grow at the bottom of the porous structure. So when we achieve a continuous value of the current density, that means that we achieved a self-organized structure. Of course, that after a first anodization, at the surface of the template, we have a non-ordered array of the pores. But then, by a selective chemical etching, we are able to remove this porous oxide layer, and we have on the surface of the metal, we have the pattern of the bottom of the pores. Then, when we perform the second anodization, we start to grow the new pores in this pre-patterned surface, and we are able to obtain a self-organized array of nanopores. Okay, then these templates, in the case of the nanoporous aluminum membranes, these templates can be used to grow materials inside the pores. I mean, inside the pores, if we want to grow nanowires or nanotubes, but we can also grow, for example, antidotes on the surface of these templates. Okay, so to fill these templates by the desired material, nanowires or nanotubes of the desired material. So first, we need to remove the bottom of the pores, because if we want to grow the nanowires by electrodeposition inside the pore, that is, I think that is one of the main used methods to grow nanostructures inside the aluminum membranes, we have to remove the bottom of the pores. We can do this in two different ways. So in the first way, we can remove the aluminum foil that remains at the bottom of the pores. And then by a selective chemical etching, we can also remove the bottom of the pores. If we want, we can also increase the porosity of this membrane, so by increasing the diameter of the pores by performing a chemical etching. Then we can put electrical contact that we can grow by sputtering, for example, and having here a conductive layer, we can fill the pores with the nanowires of the desired materials. If we want to grow nanotubes instead of nanowires, so instead of growth, a continuous thin film at the bottom of the pores, we can grow a very thin layer of the metallic contact that usually we use gold, but other metallic layers can be deposited. And in order to, and then deposit a polymeric non-conductive, like a polymer, to completely cover the bottom of the membrane, and the nanotubes will nucleate in the metal that is near to the holes of the pores, and in that case we are able to grow nanotubes. Another method that can be used that it's more easy to implement, less laborious, is the pulsed electrodeposition. In that case, we don't need to remove totally the bottom of the pores. We can reduce the thickness of these pores by reducing the anodization potential that is proportional to the thickness of the bottom of the pores. And when we achieve a very thinner layer, I mean less than 10 nanometers in thickness, we can have the tunneling of the electrons in order to reduce the metal inside the pores and perform the electrodeposition inside these nanoporous membranes. So for using these two different methods, in one we can perform DC electrodeposition, in the other we can perform pulsed electrodeposition. Pulsed electrodeposition corresponds to a less laborious method, very easy to implement, but have, from my point of view, two main limitations. It's very difficult to grow alloys. Works very well for to grow elemental nanowires, okay, but it's not it's possible, but the composition of the alloy changes along the electrodeposition due to the resistance that we have at the bottom of the pores. It's also difficult to grow segmented nanowires if we want to use a co-deposition method, and it's not possible to grow nanotubes using this method. For this, the other kind of nanostructures, it's possible to use both methods. So I will show you an example of electrodeposition of nickel nanowire is inside these nanoporous aluminum membranes using both methods. And as you can see here in the magnetic measurements, we obtain more or less the same behavior, the same magnetic behavior by using both methods. Regarding the crystallographic structure, it is also the same, but in the case of the DC method, where we don't have the oxide layer, we achieve a high grain size by performing this electrodeposition. So by using this template-assisted method, using nanoporous aluminum membranes, we are able to grow several types of nanowires of different materials, metallic materials. Then the template can be removed and the nanowires can be suspended for different applications, namely for biomedical applications where we need to have these nanowires in suspension. And we also deposited different types of alloys, magnetic nanowires, also these thermoelectric materials. We are able also to grow branched nanowires inside these nanopores, segmented nanowires of different materials. Okay, in the case of the segmented nanowires, and in particular case of magnetic nanostructures, we optimized and characterized regarding the magnetic properties of these nanostructures depending on the length and also the diameter of these nanostructures. So we changed the length of these nanowires from a disk, as you can see here, up to a high aspect ratio nanowire where we have a length higher than the diameter. And we see that we can go from an isotropic nanostructure up to magnetic behavior dominated by the shape anisotropy of these nanostructures. So we are able to completely map the spin configuration of these nanostructures depending on both length and diameter of these nanostructures, taking into account the dipolar interactions between them, since we have an array of nanowires that are near to ones to each others, and there are some magnetic interaction between them. We also performed co-deposition of multi-layered nanowires. So, for example, in that case, we grown copper nickel multi-layered nanowires, but having copper and nickel in the same solution. So first we determine the reduction potential of both elements, copper and nickel, and by performing a pulsed electrodeposition, we are able, in controlling the time of each pulse, we are able to grow segmented nanowires up to 6,000 layers of materials in an homogeneous way. And by changing the time, the electrode position time, we can also play with the length of both iron segments and copper segments. And we studied both. We studied by maintaining the length of the magnetic part constant and changing the non-magnetic layer thickness. I mean, the distance between the magnetic segments, we are able to see the contribution of the dipolar interaction between these layers. And we can go from a behavior, if we have the magnetic layers closed one to each others, we have a behavior like a continuous nanowires, up to have the behavior of the individual nanowire, as we can see here when we increase the thickness of the copper layer. We also studied these dipolar interaction by first order reversal curve diagrams that possibilitate us to study in detail the interaction between the magnetic layers depending on the distance between them. Okay, and finally, we also studied, so by using a Cooper spacer higher in order to study the individual behavior of the magnetic layers, we also played with the length of the magnetic layer. And as you can see here, we are able to grow from nanodiscs where with an anisotropic behavior, where we can go up to a superparamagnetic behavior until to this kind of high aspect ratio nanostructures with the behavior dominated by the shape anisotropy. So now let's go to the biomedical applications of these nanostructures and why use high aspect ratio nanoparticles instead of spherical nanoparticles. So because they have high surface area, we can tune the physical properties, as you can see in the previous slide. So we can, by playing with the diameter and the length, we can tuned physical properties. In the case of magnetic ones, we can induce a magnetic torque, and we can increase the time circulation of these nanostructures in the body in order to improve the treatment of these nanostructures. Also, the shape, the size, and the surface charge are very important to control the accumulation of these nanoparticles in the body and possibilitate them to use them in biomedical applications. So recently, it was reported that instead of use magnetic hyperthermia, when we move a quite small spherical nanoparticle in a superparamagnetic state, we are able to increase the local temperature and try to kill cancer cells by using this heating. Recently was reported that by using low frequencies and low magnetic fields, we can use spin vortex nanodiscs in order to perform a magnetomechanical cell death. So instead of increasing the temperature, what we can do with the magnetic nanodiscs is moving them by applying an external magnetic field and damage the cell by this magnetomechanical movement. This can be done with the nanodiscs, but also with the nanowires. So we used both nanodiscs and nanowires. First, we tested the biocompatibility of these nanostructures. So we see that we have a good cell viability up to more than 100 nanodiscs or nanowires per cell, and also more than 100 are internalized by the cell, so go inside the cell. So in principle, this number of nanostructures is enough to perform the cell death, because this, in principle, only one nanostructure can be enough to damage the cell by applying an external magnetic field. We can also combine these magnetic nanostructures with the lipid nanostructures. So you can see here in the scheme, so we have a shell, a lipid shell, and then we can put a drug inside in the magnetic nanostructure. Here we can see in the scanning electron microscopy, the white part is the lipid nanoparticle, and the black points are the magnetic nanostructures that are inside the lipid nanoparticle. We can apply an external magnetic field at different frequencies and combine the magnetomechanical effect or the hyperthermia effect with the chemotherapeutic effect of the drug. And these multifunctional applications can improve the cancer treatment. Also, in collaboration with the Hospital Gregorio Marañón here in Madrid, in Spain, we started performing the in vivo studies. So for several types of these magnetic nanostructures and lipid nanostructures, we started performing the in vivo studies using mouses as an animal model, and by using infrared fluorescence, we are able to see the biodistributions of these nanostructures, the elimination time, the circulation time, and then we are starting to use a cancer xenograft to test the effect of this treatment in vivo applications. So another advantage of these nanoporous aluminum membranes is that since we can grow layers of different materials, for example, we can grow magnetoplasmonic nanostructures. As you can see here, we have a nanowire with a magnetic material that can be nickel, but can be also iron. Now we are working with iron because it's a biocompatible material, and we can also put a segment of gold, for example, that is a plasmonic material that absorbs in the near infrared region. In that case, we use these gold nanorods or these gold nanowires for photothermal therapy. We combine them also with a drug. We put them inside a lipid nanoparticle with the drug, and then by applying a near-infrared laser light in the wavelength where these nanowires absorbs the light, and by optimizing the laser power, the concentration of the nanorods, sample volume, etc., we are able to optimize the conditions to perform these assays. We performed in vitro assays with the breast cancer cell line, and we see that we have a chemotherapeutic effect due to the presence of the drug. Also, the lipid nanoparticles is pH sensitive, so we have release of the drug, but we can improve this effect. We can improve the release of the drug by this hyperthermia effect using the near infrared light that interacts with the gold nanowires that we have inside the lipid nanoparticles. So now I will move to another type of porous membranes made by laser interference lithography. Also, in order to obtain this kind of nanodiscs that I already explained, to be used in both magnetomechanical cell death for cancer therapies, but can be also used for cell stimulation. So depending on the force that we made between the nanodisc and the cell, we can both stimulate or damage, depending, of course, on the frequency of the magnetic field and the intensity, the strength of the magnetic field. So we perform always, both in the case of nanowires and the nanodiscs, micromagnetic simulations using MUMAX-3 in order to know the spin configuration of our nanostructures, and in order to design size and shapes and thicknesses able to produce the vortex state. As you can see here, by using laser interference lithography, we're able to grow this kind of nanodiscs with more or less 400 nanometers in diameter. We achieved the vortex state, as you can see here in the magnetic measurements, and then we remove the nanodiscs from the template via chemical etching, and also we can see that we have biocompatible nanostructures with where we don't have any decrease in the cell viability, and also these nanodiscs goes inside the cells. However, the problem is that, so we also, in that case, we also perform the magnetomechanical cell death at 20 millitesla, and as you can see here, very low frequencies of 0.1 hertz. And by increasing the concentration of the nanodiscs, we are able to kill the cells. So we have to improve this method, because probably by increasing the intensity of the magnetic field in order to reduce the cell viability, but we are able to kill the cells with this magnetomechanical cell death. But the problem is that these nanodiscs go inside the cancer cells, but also inside the other cells, namely the cells of our immune system. So in order to avoid this, and in order to increase the time circulation of these nanostructures, we functionalize the surface of these structures with two different polyethylene glycol molecules. And as you can see here, we're able to decrease the cell internalization by the immune system. In that case, we tested with the monocytes, that is one type of cells of our immune system. So we believed in that case, with this functionalization, we can increase the time circulation and then increase the efficiency of this treatment. So finally, I would like to show you our preliminary results regarding the using of Langmuir-Blodgett method to produce also another type of porous templates. In that case, the main objective is to cover these some spheres with some nanoparticles, spherical nanoparticles, with a magnetoplasmonic material. So in that case, we will use iron and gold. And to do that, we put silicon oxide or polystyrene nanoparticles on the surface of water. And then we start by pressing two bars in order to have a continuous monolayer of nanoparticles in a compact way, okay? After having it, we know that we have, because we measure during the process the superficial tension of these nanoparticles, we transfer these nanoparticles to the desired substrate. And as you can see here, we are able to have large areas of self-assembled nanospheres on a monolayer of nanospheres on a surface of a substrate. Then we can grow our semi-shells on the top of these nanoparticles. In that case, we used, as I said before, iron and gold. We characterize our magnetic the magnetic part of these nanostructures. And we also performed the optical characterization in order to see if we have the absorption in the near infrared region in order to be able to use them for near infrared hyperthermia. So if we have a continuous layer of gold, we have a scattering behavior. So in that case, these kind of nanoparticles can be used as a contrast agent for OCT. If we have small iron spheres in the surface of the nanoparticle, we see that we have an absorption around 500 nanometers. So we are not in the near infrared region, but if we put a magnetic material and our iron oxide material between the silicon nanoparticle and the gold nanoparticles, we are able to make a redshift, and in that case, we have our nanoparticles absorbing in the near infrared region. So this is my main research line, the development of this kind of nanostructures based on porous membranes for biomedical applications. But I also we also use this kind of nanostructures for energy applications. And why so different applications, the biomedical and energy applications? Because playing with the physical properties of these materials, I mean porosity, multifunctionality, the enhanced surface area, all of these physical properties of these materials have advantages for both biomedical and energy applications. So, for example, porosity or enhanced surface area, it's good for biomedical application because we can better functionalize the surface of our nanostructures in order to have a target for the desired disease. But by enhancing the surface area, we can also enhance, for example, the photocurrent in a photoelectrochemical solar cell. So in fact, we are working in our work is in material science, and we use this kind of nanomaterials. I mean, the same titanium oxide is an excellent semiconductor for photocatalysis, and is also an excellent biocompatible material for biomedical applications. So there are several materials that can be used in both application, which is our case. But in fact, the anodization of iron, tungsten, and titanium is a work that I started when I was at Porto University, and now is a work led by Arleta Polinario at Porto University, and we are collaborating with Arleta. In particular, Francisco Fernandez is my PhD student, is our PhD student, and he is working with this in part of his PhD thesis with black titanium oxide for application in photoelectrochemical solar cells and in photocatalysis. These kind of materials, in particular the porous materials of hematite and titanium oxide, have several advantages and can be applied as photoanodes. And we can play with the porosity of these materials in order to improve the efficiency of these nanostructures. So the same, we obtain these nanoporous membranes or nanotubes of these semiconductors by anodization methods. We perform the same anodization method that we performed to produce alumina membranes, but we using different electrolytes, different anodization potentials that can be optimized depending on the nanostructure that we want to obtain, depending on the material, the thickness of the pore walls, the diameter and the length of the desired structures. Okay, so we developed several works regarding the synthesis of these titanium oxide nanotubes for diosolar cells applications. We played with the porosity dimensions of these pores in order to optimize these nanostructures to have a high surface area and the desired properties to be efficient photoanodes in photoelectrochemical solar cells. The same for hematite nanotubes, and with hematite nanotubes, I mean this kind of nanoporous templates, but when the pores are separated between them, and we call nanotubes, it's arrays of nanotubes, but in a membrane connected, all of them. And we also optimized the porosity of these nanostructures in order to improve the photocurrent of these nanostructures for photoelectrochemical applications. So, in the last slides, I only would like to show you another application that merges the hematite nanostructures with the nanoporous alumina membranes. In that case, we grown the iron oxide inside the nanoporous alumina templates. And when we have the dispersed iron nanowires, we converted them by several annealing steps. We converted them in a double-walled hematite nanostructures, okay, where we can see these kind of nanotubes with the double walls of hematite with very thin walls that will believe that can have a high efficiency as a photoanodes, and we can also improve the surface area if we grow modulated nanowires instead of these linear nanowires, and then obtain these modulated double-walled nanotubes. We are also using the plasmonic nanostructures that we use for near-infrared applications and biomedical applications. We can also put these plasmonic nanostructures, these gold nanoparticles in our photoanodes, and we see that the plasmonic effect can significantly increase the photocurrent of these nanostructures by possibilitating the absorption in the other wavelengths of the spectra where for example, hematite, have no absorption. Okay. So finally, I would like to acknowledge a lot of people, but in particular, I would like to acknowledge to my students, Ricardo, that just finished his thesis in the last month, Sofia, Francisco, Alejandro, and Sara, that are my PhD students, and also Belen, that is a postdoc in our group. And so this work is possible because they are always in the lab. So thank you very much to several institutions that I'm collaborating, to the projects that supports this work, and thank you very much for your attention.
Thank you very much, Celi, for this very nice presentation. So we have a few minutes for questions.
Can I ask?
I see, I see a hand.
Okay.
So, okay, please.
I have a question about plasmonic photoelectrocatalysis of chemical systems. Do you really think that plasmonic has a substantial effect on the photoelectrocatalytic reactions?
Sorry, I cannot hear you very well.
I can repeat it. Yeah. Do you think that plasmonic particles really have a substantial effect on a photoelectrocatalytic reaction?
Experimentally is what we see. So we see that when we have gold nanoparticles with absorption peak around 500 nanometers, we see a significant improvement in the photocurrent.
How significant is it? I mean, in percent. How significant it is in percent?
So, for example, in that case, we have an improvement of 50% in the current density, but we have a quite in that example that I show you, we have a quite low efficient photoanodes. In other case, in a more optimized photoanodes, we have improvements around minimum 10%, but we can go up to 20% in the current improvement.
So, if it is so efficient, so what is the main mechanism of it? I mean, for photocatalysis, you have a electron and holes that produce in the semiconductor. And what is the contribution of this gold nanoparticles to the overall experimental or let's say a process?
Yeah, so there are several mechanisms reported in the bibliography. Depends on the configuration of these nanoparticles, sizes, materials. And in fact, in the case of our work, I think that we need to combine some simulations, some theoretical studies in order to better understand and in order to confirm what is the mechanism. We are also trying to in that case, we have the plasmonic nanostructures in the surface of the semiconductor. And so we believe that these nanostructures have absorption around 500 nanometers, where the hematite don't absorb. So we believe that the absorption of these electrons can contribute to the absorption of the hematite in a wavelength where the semiconductor is not absorbing, but we are also trying to put them inside using a strategy to grow the nanoparticles inside the semiconductor in order to see if we can change this behavior and if we can play with the other mechanisms and what's happened in terms of efficiency of the nanostructures.
Yeah. From my
See
experience,
the
it's very
effects, but it's true that we doesn't understand completely the mechanism, and this is important in order to improve the efficiency.
so yeah. So again, from my experience, it's very difficult for electrons to pass Schottky barrier, and then this is not clear what exactly happened in the system. So, and from my experience, plasmonic effect is negligible regarding the semiconductor activity, for example. Yeah? So this is so yeah. So this is a good question. How it contributes to the overall
Yeah,
photoelectrocatalytical system. Right? Yeah. Thank
yeah.
you.
Thank you for your question and comments.
Any other questions?
I can ask another one. Yeah. How stable this hematite nanorods? I mean, again, in photocatalytic activity, so the reactions are very tough, and
Yes, so
photocorrosion is one of these problems.
yeah, we performed the stability measurements during 1 week, and during 1 week they are stable. So it's true that there are some works in the literature, but of course quite different type of nanostructures that reported more time of stability. In a practical point of view, sometimes it's difficult to test more time because we need to monopolize the equipment that needs to be used by other users. But so several days is stable. It's not like other materials that we see and a clear decrease of the stability in the first hours or days. No, it's stable along a few days.
Hmm. Yeah. So titanium is in general photoresistive, photocorrosion resistive, but yeah, efficiency is very low. So yeah.
No, yes, this is so the Francisco thesis is in the so I come and it's so I started with titanium oxide, then I moved to iron oxide because I'm also working with iron oxide for
Yeah.
biomedical applications because magnetite is a very nice magnetic phase and hematite is more easy to obtain. But then we come to titanium oxide. So we are trying to obtain black titanium oxide that has some advantages compared with the titanium oxide. And
For photoelectrocatalysis or for photovoltaic?
Also for photocatalysis. We are working only with photocatalysis.
Yeah.
I never worked with the solar cells.
Yeah.
But with the photocatalysis, we see an increase in 10 times in the photocurrent when we use black titanium oxide with the same nanostructures, with the same titanium oxide nanotubes, 10 times higher when we have black titanium oxide because we significantly change the band gap of these nanostructures when we convert with black titanium oxide. But the stability of black titanium oxide is another challenge.
Now you should have a process how to stabilize it mechanically, for sure, and also chemically. This is also
Yeah,
true. Yeah.
yeah.
I believe you do not breathe near this black titanium or whatever. So yeah. Okay, thank you.
Thank you very
Uh,
much.
I have just a curiosity. You mentioned the photothermal methods in the biomedical field for the nanoparticles for hyperthermia. I think I just wanted to know if these methods are modulated by amplitude or they are continuous.
So regarding
The phototherm,
we,
you mentioned photothermal methods with laser.
yes, yes,
Okay, is this modulated in amplitude or continuous?
is a continuous. We use the continuous laser,
Okay,
but we also started using pulsed laser, a femto laser, and we have very nice results because we don't see these. We don't see a macroscopic heating, but
sure.
depending on the power and the pulses, we are able to transform the nanowires in nanospheres. So we have the melting of the gold that was already reported, and we don't see for low concentrations, of course, that is the idea for biomedical applications. It's a very localized heating. But in that case, we already studied for continuous laser, we already published it, and we are starting with the femto lasers in order to see if this so local heating is enough to damage the cell or to release the drug inside the nanoparticle.
Yep. Yep. Yes, you have uh, um, a degree of freedom with the frequency of the modulation because with the photothermal techniques you are moving from a thermal regime to a plasmonic regime depending on the frequency. So
Yeah,
yeah, you can have more freedom choosing the right frequency. Yeah.
yeah,
I mean,
Luca. So
plasmonics
yeah,
is lower than femtosecond. Obviously, you are modifying the materials, but if you keep lower powers and lower frequencies, maybe you can switch from one regime to the other.
That's a very good idea. So I started this work at Porto University. I used a femto laser that are there, that is from the group of Felder Crespo. And in the case of that laser, we cannot play
Sure,
with the
sure.
frequencies.
Yeah, you
So
have so much fluence from the from
yes,
a femtosecond laser that you are melting everything. But
yes, yes, yes,
typically the old photothermal techniques are using continuous lasers and with modulators, acousto optics or something similar. And so you were ranging from very low frequencies, hertz, I mean, to the megahertz. And so you can see the different contribution because until I mean, the megahertz, the contribution is mainly thermal, and then
yeah.
you are if you have metals, you can also move into the plasmonic regime, and it's could be also interesting.
Thank you very much,
All
Luca.
right, thank you. So if I don't see other hands up, so I will thanks the speaker again. Thank you, Celia, and thanks a lot. The video will be available on the Netpore website. Oh, there is another. Okay, there is people applauding. Okay. So thank you very much, and we'll meet on during the next month for the next seminar. Thank you very much.
Thank you very much for the opportunity to share my work.
You're welcome.
Bye. Thank you.
Bye bye.
Hey Luca.
Ciao!
Hello.